Greetings, knowledge seekers. Have you ever wondered if your intuition can deceive you? Today, we're exploring a fascinating paradox. Imagine you're on a game show and have to choose between three doors, one with a car behind it and two with goats. After you make your choice, the host opens a door with a goat behind it and offers you the chance to switch your choice. What would you do? Would you stick with your initial choice or switch? If you think it doesn't matter and that the odds remain the same, welcome to the 95% of people who fall for this intuition-based fallacy. In reality, your chances of winning double if you switch doors. Want to know why? Join me to find out, but don't forget to like and subscribe to my channel first. In 1990, the person with the highest recorded IQ to date proposed a problem in their weekly column in Parade magazine, with a result so strange and counterintuitive that it earned the name Paradox, the Monty Hall paradox. This is another example of how bad our brains are at calculating probabilities and doing statistics. Don't feel bad if you fell for it too. Everyone does. Try it with friends and family, and you'll see how hard it is to understand. They might have to see the explanation 1,000 times and still cling to the wrong intuition, thinking the probability doesn't change. Not only your friends or coworkers fall for it, but even those with advanced academic training in sciences, PhD holders in physics and mathematics, also fall for it. I did too, when I first heard about it. The situation was so paradoxical and controversial that the person who uncovered it, Marilyn Vos Savant, faced the relentless ire of society, particularly the intellectual elite who collectively thought she was wrong. It's a story that's both comic and tragic, offering a lesson to be learned. While the original problem can be traced back to Joseph Bertrand's 1889 box problem, and even appeared in its original form in letters by Steve Selvin in 1975, it didn't gain popularity in America until 1990, when Marilyn Vos Savant published it in her Q&A column in Parade magazine. Marilyn Vos Savant, who became famous in the 1980s for achieving the highest score ever recorded on an IQ test with 228 points, was hired by Parade to write a weekly column answering questions. On September 9, 1990, she published the question that would give rise to this paradox. Her affirmative answer, that it's better to switch doors, caused a nationwide uproar. How could the probability change? What kind of math was this? As a result, Vos Savant received around 10,000 protest letters, including more than 1,000 signed by academics and PhD holders in physics or mathematics. Many of these letters were not friendly. You really messed up. Since you seem to have trouble grasping basic principles, let me explain them to you. Once the host opens a door, you now have a 50% chance of being right whether you switch or not. Your chances of winning are the same. There's enough mathematical ignorance in this country, and we don't need the person with the highest IQ spreading more. What a shame. You might want to get and review basic probability books before attempting to answer such questions again. Your analysis of the game show is wrong, and I hope this controversy draws public attention to the national crisis in math education. If you admitted your error, you would have constructively contributed to solving a deplorable situation. How many irritated mathematicians does it take for you to change your mind? You're wrong. But look on the bright side. If all these doctors were wrong, the country would be in serious trouble. There was also a hint of sexism. Maybe women see math problems differently than men. So who is right, Vos Savant or the 1,000 brainy PhD holders in physics and mathematics, along with all our common sense and intuition? The problem was discussed everywhere, gaining national attention. Everyone wanted to know who was right about this problem, known as the Monty Hall paradox because it resembled a famous TV show. But we want to know more. What's happening here? Let's start by reviewing the formulation of this paradox and pay attention to the nuances because they are very important. We have three doors, one with a prize. We don't know where the prize is, so we choose randomly, for example, door 1, without opening it. The host, Monty Hall, who knows what's behind the doors, opens one without the prize and then offers you the chance to switch doors. What would you do? It turns out that switching doors is the best option. By doing so, you double your chances of winning. Yes, it sounds counterintuitive, but it's true. The math shows it. How can this be when you chose the door before the other was opened? How can the probabilities change? Common sense tells us that if our initial chances of winning are 1/3, when the host opens one of the doors, there will be 2 options left. So the probabilities become 50%, 1 and 2. Although this reasoning sounds very logical, it is wrong. The error is subtle, but when the host opens one of the doors, he knows what's behind it. He doesn't open the doors at random. He opens one where he knows there's a goat, thus giving you information that updates the probabilities. Okay, I know you need more concrete proof. Here are 5 ways to break down this Monty Hall problem. Let's go. By simple logic. Let's start with the most straightforward way. When you choose a door out of 3, you know your chances of winning are 1/3. Therefore, the probability that the car is behind one of the other 2 doors is 2/3. When Monty opens one of the other 2 doors, it doesn't change the probability of winning with the first door. It remains 1/3. Thus, the remaining door accumulates a probability of 2/3, precisely double. Can't see it? Let's try another way. Counting. Let's say you choose door 1. The reasoning is the same for any other door. If the car is behind door 1, Monty will open door 2 or 3. If you decide to switch, you lose. If you stay with your door, you win. If the car is behind door 2, Monty will necessarily open door 3, so if you switch, you win. The same happens if the car is behind door 3. As you can see, by always switching, you win 2 out of 3 times. Double the odds if you decide not to switch. This seems definitive. Even so, let's propose another method to help clarify things. Exaggeration. Let's take things to the extreme and see what happens. Now we have 100 doors with 1 car and 99 goats. You choose one at random, for example, the first one. You know you have a 1 in 100 chance of picking the car, while the other doors collectively have a 99 in 100 chance. If Monty opens 98 doors, each with a goat behind it, leaving 2 doors, the one you chose still has a 1 in 100 chance, while the other door has absorbed the probability of the rest and has a 99 in 100 chance. This reasoning becomes more visual with a deck of cards. You can try this at home with an American deck of 56 cards. Pick one at random, it will be the Ace of Hearts. The probability is 1 in 56. Now someone takes the deck and discards 54 cards that aren't the Ace of Hearts, leaving 2 cards, yours and the other. One of the 2 must be the Ace of Hearts. If you had to choose, which one would you pick as your candidate for the Ace of Hearts? The one you initially chose with a 1 in 56 probability, or the other, which has absorbed the probability of the 54 discarded cards? Now it makes more sense, right? An experimental example. We won't stop trying to convince the most stubborn ones experimentally. Go to an online Monty Hall problem simulator and try it as many times as you can. You can also do it at home with 3 cups and a bean or a pebble, asking a friend to play the host. Play enough times and do the math. The number of times you win by switching cups will be about double the number of times you win without switching. The numbers show it. Lastly, if you need one more demonstration, let's do a mathematical simulation. We create a program that simulates the Monty Hall game and repeats it hundreds of thousands of times. Well, we won't do the simulation here because it's already been done. You can go to the Wikipedia article and see how mathematical simulations show that switching doors doubles your chances of winning to exactly 2/3. I also encourage you to check out Marilyn Vos Savant's 1991 column to see the story's progression. We've seen that the probability of winning by switching doors is higher, but what else can we learn from this story? The brain doesn't have an accurate perception of probabilities. Biases and heuristics strongly influence our perception and decision-making, and it's crucial to be aware of this. This can be applied to many aspects of life beyond simple probability games. The Monty Hall paradox is a reminder that our intuition isn't always a reliable guide in decision-making, especially when it comes to probabilities and statistics. Congratulations, knowledge seekers. Now you understand the Monty Hall paradox, but the curiosity doesn't end here. There are enigmas that challenge our understanding even more, revealing unexpected findings in unlikely places. Have you ever wondered how an object can be where it shouldn't be? Discover more in our previous video, where we unravel another mystery that defies logic and history. Don't miss it.